Good morning, AP Chem. Last night for homework, you had a few sections to read, and I want to go through a couple of those sections right here, right now. Let's do it. So first thing I want to do is talk about pH and solubility, and this is section 16.9. Take a look here. Let's say that we have a supersaturated solution, supersaturated because I have the solid, but let's kind of ignore this solid area, then let's call this region of the solution saturated. So we have a saturated solution that has this generic base that is XOH2. So could be iron 2 oxide, for example. Notice we have an equilibrium with this slightly soluble solid here, and we're releasing X2 positive, and we're releasing 2 OH minus in small amounts. We are given the KSP of this particular substance here, so that's going to be important. So here's the question. Write this down here. Write down the situation. And then write what is the pH of this solution. Now from your homework, I want to see if you can do this on your own without guidance here. I'll start you off. Let's write this solubility situation in a more traditional form. So I'll start you off here with X hydroxide. That would be X2 hydroxide, and that's going to be a solid. And we're in an equilibrium situation with X2 positive aqueous plus 2 hydroxide. Remember the stoichiometry here, so this is 2 hydroxide. All right, you're given the KSP. Go ahead and get started. See what you can do here. Well, the first thing is let's write the KSP expression here. So this is KSP equals concentration X2 positive, concentration OH minus. Don't forget to square that. And let me push this over just a little bit. And we'll separate it. There we go. So there's the KSP expression for this situation. Let's do an ice problem now. So I'm going to put ice here. And notice we can put a line. Let me get rid of this, get this out of my way. Notice we'll put a line right through here because that's a solid. And notice initially we're going to have 0 and 0 here. Equilibrium is going to be established within a fraction of a second. So we're going to have a change here. This is going to increase by S, so this is going to be plus S, and this is going to increase by 2S. Notice at equilibrium we'll have S, and again, this is the molar solubility, so this is moles per liter. And then we're going to have 2S. Excuse me. Well, notice here we have S for this cation here, and we have 2S for the hydroxide. We have the KSP expression here. Let's simply take our equilibrium values and substitute them in here. And then we have this, we have KSP equals S 2S squared. So that was easy enough. Here's our equilibrium. amounts, and we're plugging it in here to the KSP expression. Well, notice, take 2s and square it, and then times that by s, so we'll have KSP equaling 4s cubed. We know the value of KSP here, it's given for 25 degrees Celsius, so let's substitute in this value here. So we've got 4.00 times 10 to the negative 11th. That equals the KSP, and that equals 4s cubed. Now it's simply now, of course, you've left math and you've entered freshman algebra here. Wait, that didn't come out right. You left chemistry and you've entered freshman algebra. So we're going to solve for 4s now. Or I'm sorry, we're going to solve for s. I'll get it together. All right, so here we go. 4.00 times 10 to the negative 11th equals 4s cubed. Let's solve for s. We've got 4.0 times 10 to the negative 11th. Let's divide by 4. And let's take the cubed root of that. That will give us s. Let me plug that in the calculator, see what we get. So, s is 2.13 times 10 to the negative 4th. Let me just recheck that. And that is our value for s. Now we want to determine the pH of this solution. Be careful here. We have solved for s. S is the molar solubility of our double positive generic metal here. So we've solved for s. You want to solve for 2s. Then, no rookie mistakes here, no rookie mistakes. Then we know that 2s is going to equal our hydroxide ion concentration. We can then figure out the pOH, then figure out the pH. Don't forget, you solve for s. This is, hydroxide is 2s. Give it a shot. So will I. All right, so here's our s value. We've got 2.13 times 10 to the negative 4th. Let's go ahead and times that by 2, and that gives us the hydroxide ion concentration in moles per liter. So we're going to get 4.26 times 10 to the negative 4th here. And again, that's our hydroxide ion concentration. Then we'll simply take the pOH. So the pOH equals 3.37. And let's subtract that from 14. So and we're going to get a pH of 10.6. Let's get in good habits of boxing our final answer here. Let's go back and take a look at sig figs now. So we have 10.6 here. Does this answer make sense? I think it does. We want a it's a basic saturated solution here. Let's go back and look at sig figs. People, on the AP test, and we'll talk about that at a different time on a different video, but on the AP test, you will get nickel and dime to death if you don't worry about sig figs. As you do calculations, minus half, wrong sig figs, minus half, wrong sig figs, all the way down. Don't let that happen. Go back and look at your original data. Is this what we're using for sig figs? No, we didn't throw in temperature here, so no, it's not 3 sig figs. but we did use this in our calculation. So there's 3 digits. Our final answer cannot be any more precise than our least precise measurement. So that looks fine to me. That is the correct amount of sig figs. All right, so now I want you to do a problem. So go ahead and, here you go. pH of a saturated solution of iron 2 hydroxide. Here is the KSP of iron 2 hydroxide. Go ahead and do that now. No peeksies. Flip that page over. Don't look at this. You need to be able to go through it on your own without any guidance here. All right, mark it set, go. All right, so here's the equilibrium situation here with our iron 2 hydroxide. Notice the KSP expression here. So KSP expression. Of course, never hurts to stay systematic, so we'll just go through the ice method. Again, if this is redundant, I want it to be. I want you just to get used to doing this, and this will actually be a good way to start for the more tricky problems as well. So hopefully the problems that we're doing now are more straightforward for you. But if they get a little trickier, you'll have to set up ice and kind of reason some things out possibly. Anyway, let's go initially here. We're 0, that's got to be plus S. That's got to be plus 2S at equilibrium. Obviously, again, S and 2S here. Let's plug in these S values here. And again, we're going to get this situation. So we want to show our work here. And we're going to have 4s cubed equals the KSP. The KSP value is 1.6. 1.6, is there another digit over there? 1.60 times 10 to the negative 14. So we're going to solve for S. So we have S equals 1.60 times 10 to the negative 14. We'll divide both sides by 4. We're going to take the cubed root of that. So the cubed root is a second function on your calculator. Calculator people, you got to know how to use your calculator and you know who you are. All right. So there's my S value. Now I did this quickly. We've got S equals 1.587. Notice I'm extending this out past my sig fig value because I can round at the end, and that's times 10 to the negative, let's see what it is, 10 to the negative 5th. So that's my molar solubility. I could have asked what's the molar solubility of iron 2 in this saturated solution. And there it is. That's molar solubility. Let's make sure we put big M here. So moles per liter. The only thing that doesn't have units here is these KSP values don't have units. Well, anyway, I want to figure out the POH first. So let's figure out, well, actually, it's back up. Let's figure out the hydroxide ion concentration. And then we'll figure out the POH and then the pH. So here's my, this is my S quantity. We're going to take this times 2. And we're going to have this 2S equals 3.175 times 10 to the negative 5th. That's big M. And notice that equals my hydroxide ion concentration in moles per liter. So take a look at that. Notice that value there. That value here is that concentration in moles per liter. So then we'll go with the POH. Looks like it's 4.4 0.498, and then we'll get the pH. And the pH is 9.502. Again, I was just wanted to remind you of the fact that as you're doing typical calculations, whether it's engineering, whether it's physics, whether it's chemistry, take any of the sciences here, it's a good habit to keep more digits in your calculation as you're going through this, and then round at the very end so you don't have any sort of rounding error, okay? So let's do that. Let's go back and see what we got here for sig figs. It looks like my KSP has 3, so I'm going to make this my final answer. Typically on the AP exam, typically it's going to be 3 sig figs, and when in doubt, put 3. They'll give you plus, or at least they used to do this. They've kind of reorganized the grading, but they used to give you 1 digit too many, 1 digit too few. So 3 is a good number. But of course, there's nothing like doing it the right way. Going back, last step is going back, look at the original question, then round appropriately. So, I hope that was helpful. KSPs and solubility and pH. Question. This is really slightly soluble. Obviously, let's look at the KSP value. That KSP value is very small. Question, write this question. What would the effect of adding an acid to this saturated solution have on the solubility of this substance? What would the effect of adding an acid to a saturated solution of this substance have on the solubility? Would it increase solubility? Would it decrease solubility? Or would there be no effect? Justify your answer here. Give it a shot. All right, so here's the situation. We've got this this supersaturated solution here with partial ionization of these 2 ions in solution. What we're asking is if you added an acid, would this increase the solubility of that? What do I mean by increasing solubility? I mean getting more of this to dissolve as ions. In other words, I'm asking about if you add an acid, would this equilibrium shift in that direction or back in that direction? Well, this is classic, again, classic Le Chatelier's principle here. Notice, if we add an acid here, that acid is going to react with H positive is going to react here with the hydroxide ions, and we might as well keep the stoichiometry, and then we're going to get 2 H2O water molecules there, and I just kept the stoichiometry consistent there. Anyway, obviously the acid reduces the concentration, so it reduces the concentration in moles per liter of the hydroxide. So we've disrupted the equilibrium by reducing OH minus concentration. We know that because of this stress on the equilibrium, we're going to shift to relieve the stress, and we're going to get more and more of this iron 2 hydroxide to dissolve. Now, if you keep adding more and more acid, here's what you're going to see. So let's do this. Let's add the H positive here. And we know that this is going to shift in this direction. So notice the size of the arrow. More of this is dissolving. It's becoming more and more soluble. So as you add acid, notice you have less solid. The more acid you add, the more this dissolves. So now we're still adding acid. We're not in equilibrium at this point. We're still disrupting the equilibrium by adding more H positive and then more H positive. And at some point here, notice we've added enough acid where all of this is now going to be neutralized, and we're going to have essentially water in here, H2O, plus excess acid, excess H positive, and we'll still have plenty of these iron double positive ions floating around in solution. If we measured the pH of this, the pH obviously is going to be less than 7 now because we've added enough acid to completely dissolve that solid iron to hydroxide. All right, let's say we have a saturated solution of the barium fluoride. And now what I want you to do is make a prediction here, justify your answer. We've got this saturated solution. What would the effect be on solubility now? The effect on the solubility, and when I'm talking about solubility, we're talking about the amount of ionization that's going on here. What would the effect of solubility have if we added an acid to a saturated solution of barium fluoride? Everybody, make a prediction. Increase, decrease, stay the same. Justify your answer. Go ahead and do that. All right, so here's my solid barium fluoride down here at the bottom. We have partial ionization going on here. What's the effect of adding an acid? Well, what we're asking here is, do any of these species here, these ionization species, do they react with the acid? So we add H positive here, so we'll do H positive in red here. So would H positive react with this? Of course not. It's not going to react with the barium double positive. Would it react with F minus? So really what we need to realize is F minus a relatively strong conjugate base? Because if it is, it's going to react with it. Is F minus a relatively strong conjugate base, or is this a neutral species? Not going to be an acidic species. Well, if you recall, if we have HF, HF is a weak acid. It's going to ionize partially here to H positive plus F minus. Of course, this would be a Ka situation. And just to review, we could put our Ka expression here where these products are going to go here and HF aqueous is going to go here. These are all aqueous, of course. Anyway, weak acids have a relatively strong conjugate base. So this has basic properties, basic in blue. Again, it's basic relative to water. So would this, I can change the color now, this is F minus has basic properties. So now notice this would in fact react with F minus. So if H positive reacts with F minus, that would decrease this concentration. And notice here, again, it's going to shift the equilibrium in this direction, and solubility is going to increase. So this solid down here at the bottom, which is the barium fluoride solid, is going to start becoming more and more soluble the more acid you add. So, kind of cool. Notice here, this is magnesium hydroxide. What would be the effect of adding a base to this? Go ahead and answer that. Is solubility going to increase? Is solubility going to decrease? Or is solubility going to remain unchanged? Give that a shot. I like that blue color there for that base. Of course, while you're doing that, you could have Kb value here. Kb expression, just reminding you. All right, so here's my saturated solution. Here's my solid magnesium hydroxide. Notice here's the equilibrium written out in a more traditional way. Notice, if we're going to add a base, what's that going to do to the solubility? Well, let's see here. So let's add a base, sodium hydroxide, let's say. Sodium hydroxide is 100% soluble. The Na positive is not going to influence any of this. That's going to be neutral. What about the OH? By adding the sodium hydroxide, this is going to go up now. Notice, if this goes up, the equilibrium is going to shift again. Classic example of Le Chatelier's principle. We've had a lot of those. I realize that. Lots. Your final exam. It's going to be all over the place. And by the way, we're preparing for the AP test, but we are also preparing for my final exam. This is really important, really important. So notice this goes up. This is a good example of the common ion effect. We've added sodium hydroxide from an outside source. The hydroxide ion goes up. The equilibrium is going to shift in this direction, reducing the solubility of this substance. Okay? Good example of the common ion effect. Whenever we add a common ion from an outside source, we're going to see this happen. Let me grab this. Let's say, let's start over here. We're considering the same substance, the magnesium hydroxide. What if we're going to add, let's go with magnesium chloride. So let's add magnesium chloride. So there's our magnesium chloride salt. We're going to add that. Into the container here. Notice it's going to ionize, and it's going to release magnesium double positive. So this is added, common ion. This is going to go up. Again, this magnesium ion is going to result in a decrease in solubility because we're going to shift in this direction, and we're going to have less MgO2 ionizing here. Now, what's the effect of the Cl minus? So notice we also have 2 Cl minus aqueous in terms of in terms of which came from this solid salt. Is that Cl minus going to react with this? Of course not. Cl minus is neutral in its basic properties. It's neutral, remember? Cl minus. That's the conjugate base of hydrochloric acid. So hydrochloric acid, strong acid, it's going to have a negligible, its conjugate base, Cl minus, is going to be negligible. I need to spit that out, okay? So that has no effect because that's neutral. So this brings up the concepts that we've done in a previous video here. Is the Cl minus going to react with OH minus? Of course not. All right, so that's some important concepts. What I want to do now is take a closer look at magnesium hydroxide. So that's what we're going to do now.